All right. All right, guys. Welcome. Welcome to ASRG World Webinars, bringing you the latest in automotive research, innovation, and education. My name is John Heldreth. I am the founder of Automotive Security Research Group, and we have a great presentation for you tonight. First of all, let me quickly introduce myself. As I said, my name is John Heldreth. I am the founder of Automotive Security Research Group, or ASRG. I've worked in the automotive industry for the last 15 years or so, and now focusing my time on product or vehicle security. I'm originally from Detroit, Michigan, in the US of A, but today I'm living in Germany and working at Porsche Engineering. Please feel free to follow me on LinkedIn or other social media platforms. Just quickly, I'd like to introduce Automotive Security Research Group. This is a nonprofit company focusing on the advancement of the automotive security industry. This is a community to support the coming together of two areas of competencies: the IT security market and the automotive market. This is a community for you, for the automotive engineer, for the IT security specialist, the beginner, the hobbyist, even for the people that might be in the wrong YouTube channel. Please stay here. This is a community of volunteers. Our entire organization is built not only on the volunteer efforts of the administrative team, but also, of course, from yourself, from the members. We're trying to remove the boundaries that can occur in the automotive security industry. This could be communication, borders, locations, finding ways to learn new things, or discovering new solutions, making good decisions, because at the end of the day, we all have the same goals: to keep our customers, to keep our families and our friends' data safe and secure, which can only be achieved together. If you want to get more involved, make an impact on the industry, start your own ASRG location, participate in a technical committee, or be a part of a project, please reach out to us. You can find out more about ASRG at www.asrg.io or send us an email at hello@asrg.io. Just quickly, I'd like to show you how many different ASRG locations we have currently, because we're continuously growing. Here you see an overview of the different locations that we have. We have currently 32 locations, and I'd like to introduce our newest ASRG location, ASRG CBG in Cambridge in the UK. So if anybody's joining us from Cambridge tonight, please welcome. We're so happy to have ASRG in Cambridge, and looking forward to what we can do in the future together. Now, we have around 5,100 members as of today, but we're always expanding. If you guys, if someone sees an opportunity for a new location or opportunities where we can work together to help support the industry, please let us know. Send us an email, get in contact with us. There's many ways to do that, so I think I've listed them in the description in YouTube. Check it out, get in touch with us. All right, well, we have some really great webinars, not only the one today. So not next week, but September 27th, just in a few days, we have AJ Khan, and he's going to be presenting at Cyber Talents. And he's going to be presenting about what is required to work in automotive cybersecurity. Okay, how to get involved, what you need to know, who to know. So really going to be an interesting talk to kick off the cybersecurity month in October. October 8th, we have a presentation from eScript from Kevin Henry, an overview of privacy-preserving credential management for V2X communication. That's a mouthful. Really going to be an interesting discussion here from the experts at eScript. October 15th, LibreCAN, automated CAN message translator. This is going to be really interesting as well. All of these different tools and stuff. Merit Pese from University of Michigan, almost my hometown, will be giving a presentation about this automated CAN translator tool. October 22nd, APMA IAC will be presenting a little bit different view. So not only on the product, but also on the supply chain. They're going to be talking about securing the complete mobility ecosystem. So as I said, not only the product, but in the entire ecosystem, including supply chain. October 29th, putting the brakes on cyber attacks targeting connected cars. If Ken Monroe is going to be giving this talk from Pen Test Partners, this is going to be a great talk as well. If you know Ken Monroe, he's really good at getting technical, really good at knowing his field of expertise. So come join us for that. If you guys would like to give a talk, if you have an idea for a talk, if you want to just recommend someone for a talk, send us an email, cfp@asrg.io, and then we'll get in contact with you, get you ready, get a place reserved, and talk to you about what makes sense. Very good. Okay, that's enough from me tonight. We have really a great presentation for you today. We have Mustafa. He's the CTO of AT Instruments, and he's going to be taking us through AI-based security and safety anomaly detection. So talking about detection mechanisms and so on. So Mustafa, welcome to ASRG. Please go ahead. I think you need to share your screen first. Or Mustafa is not there, maybe. There we go, Mustafa. And you sharing your screen, and you are live. Welcome to ASRG. But I can't hear you still. Are you muted?
Yes.
There we go.
Yep. I'm sorry. So thank you, John, for your intro. Hello, everyone. So very pleased to introduce my company, Autonomous Instruments, AT Instruments for abbreviation. So our product is Cpyr, and it's an AI intrusion detection system. Now, before we go to our product, we need to talk a little bit before about what's actually at the market and why we think that the next step is an AI IDS. So I'm going to talk about first about the attack surface of the automotive, just a quick brief. Then we're going to talk about any kind of an attacker, what he will do to attack or to use this attack surface. Afterwards, we're going to talk about the recent attacks. We're just going to give a brief glimpse about the white hat attacks. Now, we're going to talk later. Now, afterwards, we're going to talk about the fleet security management, the conventional one that's used by most of the OEMs, signature-based protection, the ones that everybody is using currently, and the logging for such signature-based countermeasures. Then we're going to talk about the problems and traditional mechanisms. So what's wrong? What's really wrong with these logging systems? And then we're going to talk about the AI IDS, and how can we generate data sets using the SOTIF. And first, of course, we need to define the SOTIF. It's well defined, of course, but we're just going to brief everybody about it. Then we can go to our product and we can talk about what Cpyr can really offer. And if no one can believe us, then we're gonna give you guys a demo and a recorded video for a simulation. So, so first, let's talk about the attack surface. As you all know, that during the last decade, there was hundreds of attacks on cybersecurity, but how? On automotive industry, of course, but how? First of all, we need to know that there are more than 90 ECUs in some cars. All of these cars have millions of lines of codes, and to make things worse, or even better, there's more connectivity. So there is V2X, V2B, V2I, and so on. There is mobile back-end communication over OVTP and MQTT and diagnostics, of course, through this is with the back-end server, which is normally the OEM. And of course, the normal application. So of course, there is the connection with the OEM, and there's always this cloud-based communication, and there's always the jeopardy of a man-in-the-middle attack. There is an attack over the downloads, the downloaded apps. There are sniffing of the user password on the head unit. There are malwares as well that could be introduced through multiple ports at the head unit. There could be malicious firmware updates. There could be an attack, the famous attacks on buses. There could be a compromised sensors. We're going to talk about this, and we're going to talk about some attacks that could happen through mobile attacks, of course, because now multiple connectivity, multiple cars now have mobile apps for access. And attack, of course, on the key store itself. So every ECU now has a key store inside. Not everyone, but the most cybersecurity related. So let me talk. We're going to talk about this also. So yeah, we're expecting to have a high autonomous cars really soon. We are gonna, and the most dangerous ones are of level 4 and 5. The very high autonomous levels could be expected at 2030 with millions of cars. We are going to expect also by 2025 for about this huge number of cars with different connectivity available. So so this is the jeopardy. So let's talk about how any attacker could actually attack our car. Now we have to first understand that there is layers of car communication, and accordingly layers of attacks. So first is the telematics control unit. So telematics control unit, most of the cars now have it, and it's connected to the OEM cloud, already also to our smartphones. And this is the main gateway or the main communication to the car from a remote location. Given any attack on this is the most dangerous, because if someone is planning for a fleet attack and not a certain car, then you most probably will be involved with telematics control unit. Now we go to the perimeter of the car, and the perimeter of the car here is most probably it will be the infotainment or the sensors, such as the camera sensor, radar sensor, different ultrasonic sensors, tire sensors, and key start, the passive entry, passive start. All of these are different communication. There are more as well, Bluetooth and everything. So, and of course, the very conventional attacks that could come from the OBD. So, given all of these, which are all related to the perimeter of the car, so someone has really to be close to the car to start this attack. And once he gets inside, he can actually start getting in the network, of the car network. Now, before we go to the car network, let's talk here a little bit about the protection for this layer. So protection for this layer is for the egress and the ingress. So basically, most of the OEMs now have introduced IPsec TLS communication. So mostly to encrypt the data here. Now, the other side, there has to be a firewall. So a firewall connection, which is at the other side here, and this is actually to try to prevent any kind of communication of malicious communication to enter the vehicle. Now, once the attacker enters this network, most probably there will be the gateway. Everybody knows that. So the gateway is simply a switch, and more or less, and the switch is actually connecting the different intercommunication between the different domain networks. So body domain network, powertrain, chassis, and so on. And given such interdomain communication, trying to limit and privatizing the communication as much as possible and is very important. So you need to put, for example, do some kind of tunneling or do some kind of whitelisting or try to do different kinds of mechanisms such as VLANs. So yeah, so trying to really make the communication as deterministic as possible. Now, something else, once we start going to this level, we need to introduce authentication between the different ECUs. Most probably it will be message authentication MAC. So most of the CAN messages communicating between the different interdomain will always have a message, a MAC. Of course, it's very costly, and we'll talk about this as well. And my colleague will talk about it also. So, adding this layer, there will be probably the gateway will be a client, and it will always update the key groups to the different networks, to the different ECUs. Now we go to the ECU level, and for the ECU level, we will talk about a lot of mechanisms, but basically the main ones are the ones related to the host. So trying to do MPU storage protection, trying to do secure boot, secure download for the software, and trying to do some kind of whitelisting as well for the communication. So and then we're going to talk about this really in details. So basically, these are the 5 steps to try to access a certain ECU. And you can, the attacker could start from any of these stages, but the most dangerous ones or the most massive attacks will come from the remote ones. Okay, now what we are offering, or what's missing, is an IDS, intrusion detection system. So intrusion detection system could be introduced at the gateway level, could be introduced at the domain network level, or could be introduced at the ECU level. And basically, as we said, there is signature-based detections, which are well defined before production, and the ones that we're going to talk about, our product, is a layer above, which is machine learning. So this is basically what we're going to talk about as an intrusion detection system. So very brief glimpse about the recent attacks. So 2019, the Tesla Model 3, just the car that is very new, it's quite new. So these guys were actually were able to go through the web-enabled infotainment system and actually access the network. There are, of course, not everything is disclosed. So yeah, and also just a couple of guys as well. A researcher just was actually able to manipulate the sensitivity of the FCW and AEB autonomous electronic brake and forward collision warning, and accordingly he was able to actually dysfunction the collision avoidance system. Okay, now the big picture for the fleet security management. So majorly, the major OEMs, or most of them, are now having their own complete infrastructure for security. So, so these are the signature-based defenses. So a quick idea about them. So whenever we want to detect a threat, you have to prepare a log per car. And to prepare a log per car, what could be the contents? It would be mostly about safety violations, weird resource consumption, diagnostic access requests, indicators of compromise, which we will talk about in the next few slides, and as well as, of course, if there's a firewall or IDS. And as we said, it may be an OS. At the ECU level, it may be a firewall. At the TCU level, it may be an intrusion detection system. At the gateway, maybe the gateway itself, there is some kind of weird network or weird packets going from one channel to another, from one port to another. Watchdog diagnostic requests that are not very acquainted with. All of this are set in a log, sent, for example, on MQTT, one of the very famous telematics protocols for IoT, and over TLS or IPsec. All of this is sent to a secure log, on a secure log, then sent to the incident event management and the SOC of the security operation for this OEM. They start analyzing, making a case, make an incident response, and then once a threat has been actually analyzed and it is really identified, then a software download or an update package would be prepared, and there would be a software download or OTA or OTA or SOTA software OTA or FOTA as firmware over the air. It's basically over the air updates. And these and all of these measures would be updated. Okay, now we have talked about the infrastructure. Now let's dive a little bit deeper. Now, protection methods, there are two major protection methods. So we talk about certificate or public key based protection, and host and OS based protection. So when we talk about certificate based protection, then we'll talk about secure boot, secure software download, and so on. And this is basically based on having a root certificate, which is
well, it looks like we've lost Mustafa. Let me just... Let's just wait a second here. Sorry about the technical difficulties, but once we get Mustafa back on the line, we'll continue with the presentation. Just 1 second. Maybe quickly for those that missed the introduction earlier, we have a lot of different projects going on at ASRG currently. So actually, one of the biggest things that we're working on right now is the web portal for members. So we have all these great resources for everybody, right? We're talking about documentation, research, discounts for tools, licenses. We're even going to have the intelligence platform on there as well. All of this stuff will be available for members free of charge, of course. And we're working on the member portal right now. So if you're interested to help support ASRG, maybe in a project such as the member portal, please get in touch with us, get in touch with myself, and then we can discuss that. I think Mustafa, are you back? I'm not sure. Can you share your screen again? And
Okay.
I think you were discussing about the slides. If you
Yeah, just
all right, just to shortly finish what I was saying. Shortly what I was saying before, if you guys want to get involved in projects with ASRG, come join us, get in touch with us. We have lots of stuff going on, okay? So Mustafa,
okay,
there you go.
John, can you hear me?
Yes, sir.
Hello? Okay, that's great. So
one slide back, I think.
So one slide back, this one?
That's not signature-based protection, but one more back.
So we have the recent attacks, the fleet security management, big picture for the fleet security management. Is that so on?
Mustafa, your screen is not updating fast. Okay, so yes, here, big picture of fleet security management. Just start from here, and then we can fix it later.
Okay. So I explained this and the software download, right? John, can you hear me?
Yeah,
stopped here, right?
I don't remember the software download, so just go ahead and re-explain this slide.
Okay. So let me re-explain it. So we had the signature-based defenses, which were stuff like safety violations, resource consumption, diagnostics, and fault DTCs, firewalls, and all of this stuff. So all of these are signature-based defenses, which are indication of that somehow things were compromised, and there is an attack, and a complete log had been prepared. And a complete log had been prepared with all of the, whether it is an OS-based detection at the ECU level, whether it was a firewall or an IDS or a gateway problem, all of which were related to the level of the gateway or the body domain controller, diagnostic or watchdog, again at the ECU level. So once this complete log had been prepared and sent to the incident and event management backend server through MQTT, which is a very popular IoT method, IoT protocol, and over TLS to encrypt it, or IPsec. This log would be sent to the incident and event management backend server. The incident and event backend server will make a case, analyze it, try to do this incident report and check if this was an incident or at one car or at an entire fleet sent, and then at the threat intelligence, there will be some kind of a signature. The known badge will become signatures, and these signatures will be used using software download or OTA, SOTA, FOTA, software over the air or firmware over the air. It will update these signature-based defenses with the new signatures that had been identified. Okay, so basically this is the normal or the actual conventional method of protection. Now, once we have defined this, now let's go a little bit deeper. So we talk about the signature-based protection. So signature-based protection, we have two protection methods, two base protection methods. One is based on certificate or public key-based based protection. Other is an host or an OS-based protection. Now, certificate or public key-based protection is based on that there's an ECU and there's an OEM server. There's a root certificate, common root certificate identified. And of course, there's a certificate tree or certificate chain. And now the certificate authority at the OEM server would, at the start of the communication, would send a leaf or an app certificate to the ECU host. The ECU host will verify this certificate, will make sure that it's and verify that this is the OEM that it's talking with. Of course, there's the cybersecurity management manager stack, which is very well known now at the AutoSAR. And once this is verified, the certificate is verified, then there are multiple things that you can go from this step forward. Try to generate a key through a random number generation for this session. Try to sign a command and from the OEM, so the OEM server could send a command over the MQTT or over the different channels to the ECU host, and hence it could do commands over like OVTP commands, like UDS or whatever kind of commands that the OEM server would like to do to the ECU host. Now, the other method, John, is the connection okay? Before I go to the host OS.
Yeah, I think so. Which slide are you seeing?
So we are still in the signature-based protection. So
okay,
is everything fine up till here? We're gonna go to the host OS, please.
Yep, go ahead.
Okay, so I'll continue. Okay, so for the host and OS-based protection, we have here the static IP or MAC address whitelisting. So having a static static well-defined IP and MAC per port, doing secure debugging, doing memory hardening or watchdog or address-based randomization, all of which are trying to make sure that the program flow is going well, and monitoring that there are no processes or tasks that the order of the tasks is going well, the scheduling is working well. So just a quick example. So we have a software with multiple apps. These apps are distributed per core, core 1, core 2, and so on. So core 1 and core 2 and so on. And there's also the interrupt service routines distributed as well. And now we have the app, and so we have app 1 and app 2. So app 1 has multiple tasks, task 1, task 2, and so on. App 2 has task 3. Now, what the MPU could do as a protection, and it's actually a safety and a security based protection, that you try to do an isolation method between at the RAM at the stack. So, for example, you define a certain RAM area for task 1, define certain area for task 2, maybe define that the tasks, that critical tasks or the safety relevant tasks or the security relevant tasks to a certain space, a certain private space, where you're going to, for example, use the keys to decipher something, or the private key, for example, if there's a private key at the car, to that would be deobfuscated and somehow regenerated again, or regenerated again. All of this has to be done in a separate RAM area. Now, once this task is done and the scheduling or the context is being switched to another task, the MPU will handle that this space, this address, is no longer available and no one can use it while the context has been switched. Now, once the task 1 again returns as scheduling is scheduled, then this space of RAM will be available again. Okay. So we talked about the different signature-based protection. Now let's talk a little bit about the code itself. So all of these protection, for example, TLS, IPsec, or whatever kind of protection is eventually written in C. So if the C code itself is vulnerable, then whatever kind of mechanism you're going to do is vulnerable as well. So, so there are many protocols many standards. Most famous ones are the CertC, and there's Mesra-C as well. And for example, CertC has like 99 rules of coding standards. Violation of such coding rules means that there is a safety or a security potential vulnerability. Yeah, for example, we have for preprocessor like 3 rules, integer 7 rules, and so on. There's as well recommendations to improve safety and functionality and security. So, so basically, it's not enough to have a good mechanism, but as well a good coded mechanism. Now, going to the signature-based detection. So for signature-based detection, now we have talked about the signature-based protection. Now let's talk about what will be logged. So the car now is preparing a log and it's going to send it to the back-end server. Now going to sending to the back-end server, there will be what will be logged. So for example, network-based stuff like frame latencies, there's some problem at the latency of the messages. There are authentication failures. There are false freshness value for the message authentication. There are unidentified message IDs, signal out of range, diag access failures. So all of these stuff will be network-based. There are as well. There are host-based, which are like control flow, CPU time, over execution or something, over CPU overload. There are memory consumption or memory dump or core dump. All of this needs to be logged. MPU exceptions, elevation of privileges for the OS, watchdog firing. All of this, stack canaries for stack overflow, and all of this will be logged. And there's of course the key related stuff. So the key based stuff like the MQTT certification failure or the wrong verification of a certain token. All of this will be logged and sent to the per car to the OEM, and it's up to the back end server to process this as fast as possible and try to establish if there is any kind of attack occurring currently. Okay, let's talk now. We have talked about the signature-based protection. Now let's talk about the problems of these traditional mechanisms. So first of all, there is a lack of contextual understanding. This means that the consistency and plausibility is not well handled. So what is the problem? So let's give an example of this. If the car is in 1 second, it is 10 kilometers per hour, the message sending 10 kilometers per hour. Suddenly, in the next second, it is 100 kilometers per hour. Most probably, all of these signature-based protection wouldn't fire an alarm. There's nothing wrong with it. However, as a contextual wise, it's not reasonable that in 1 second, there's no car that could do such acceleration in 1 second from 10 to 100, even a Lamborghini wouldn't do that. So it's not possible. And or another problem, for example, regarding plausibility as well, that somehow the speed is accelerating. However, as a plausibility, there's a problem that the RPM is not increasing at all. And this is another problem. It's, for example, it's stable at 700 RPM since it has been ignited, since ignition, and it has not increased at all. So these kind of problems wouldn't fire any alarm. So this is a problem. Second problem is that so preparing such a log, sending it, and then making the analysis at the backend server, and doing establishing a signature, and then updating the signature back, all of this is time. And of course, if there is a compromise at one car or a fleet, most probably every second in delay is a problem. It could cause damage, or a huge problem. It could be a life-saving problem. So third is that, of course, all of these logs. So when you ask for more detailed log, as you go in a more detailed log to establish a certain attack signature, then most probably you will need more storage at the backend server, and you will need a huge processing power to do that. So so how is Cpyr? Now let's talk about the solution. Now, how Cpyr solves such problem? Beside the signature-based, we are introducing a new level of AI machine learning based technique, and this is done through analyzing the sequential behavior and the timing behavior of the car before deployment. So during production and before deploying the car to the market, there is a model would be trained inside the car. And once this model is trained inside the car, and the model is mature enough, then it will be deployed. And this model it will be running on a GPU. So and comparing the actual behavior of the car, the current behavior of the car versus the model, and if there is any kind of anomaly, it would fire it directly. So how this has solved this could be implemented inside the ECU, in a gateway, or at the TCU level. So yeah, you can pick the levels that you want. Now, once you do this, so what kind of objectives had been fulfilled? Number one, the limited time for contextual anomaly detection. So it will be in a matter of seconds, this anomaly could be detected. It's easier for forensic analysis because we have built this graphical interface that you can actually see the car behavior in a graphical way, or the ECU behavior in a graphical way, and it could send the detection. It could send. So you will see it very visible, and we're going to see it in the demo that it is very visible to the SOC operator to see that there is some kind of a behavior anomaly. There are the Cpyr has a delta update capability. So if there is a tuning needed, it could be tuned over the air, over the cloud, with no problem. We have a video for that as well. Let's continue. And as adaptive AutoZAR is becoming more and more a concrete topic now, and it will be soon introduced to the cars, adaptive AutoZAR is based on modifying the runtime environment, and this is actually due to that there are more and more machine learning models, and the machine learning models keep tuning as a behavior, and accordingly, intrusion detection system with a machine learning capability will be more and more needed with adaptive AutoZAR. Okay, now how do we build this? Now, in order to build a machine learning algorithm, you need to have data sets. So, and in order to have data sets, you need to have scenarios built. Now, to make scenarios, SOTIF, which is safety of the intended functionality, introduced in 2019, is a safety standard, of course, and it targets of building scenarios, safety relevant scenarios that the ISO 26262 wouldn't cover. So ISO 26262, for everybody who are working with safety, it's regarding systematic failures, electric failures, and so on. However, SOTIF deals with two major topics: whether there is a misuse from the driver, so the driver there's a user confusion or user overload. Second is insufficient situational awareness, which means that as the car is more autonomous now and more depending on sensors, then accordingly, if there's a problem at the sensor perception layer, or at the sensor perception. So, for example, if there is something that there are, for example, a certain holes at the road, or certain certain shadows, and the sensor has a wrong perception on that, then these problems, which wouldn't be handled at the normal safety standard, is actually need to have scenarios at the SOTIF. Okay, now how do we build scenarios that according to SOTIF? So SOTIF, as a standard, introduced that there should be a scene, a snapshot of the entire area. So think about it as a picture. And so a car and another car, and they're moving adjacent, and there's lane distance is so on, and there are trees and so on. So the entire snapshot. Now there are goals which we want to achieve throughout this driving scenario. Now, given this, there's a situation, and this situation, there's a driving functionality which is under test or under focus, like AEB, ACC, and so on. And this driving functionality is making a certain action. This action combined with the scene and an event which says, for example, that there is a problem that could occur at the action coming from the AEB or the AC or whatever, or that an event that wouldn't affect it. So we just make an event at this level to and add all of this, and this will produce the next scene, and so on. So we keep going on and on and on, and having more and more and more scenes. Now, once you build all of this tree of scenes, you can start building your scenarios given scene 1, scene 5, scene 8, and so on, and you build your entire scenario. So yeah, let's take a look at our demo or our example for what you're going to see later. So given that this is our car, the red one, and it's moving, and there is an LKA, lane keep assist, and you're moving at this lane, and but there's a problem at the car which makes the cars divert a little bit, and the LKA normally would return the car back to its ideal position in the lane. However, since there is a cyber attack that had disabled the LKA, a problem had occurred. Now, in order for this to actually be built in a SOTIF, so we spoke generic. Now, in order for this to be built in a SOTIF way, you have to, as I said, you have to build it in scenes. So to build a scene, you have an occurrence, a problem of a probability of exposure, a severity, and a probability and controllability. So here is the first. So the LKE is enabled and the car wheels aren't perfectly aligned. So there is a lateral shifting in the car position. The LKE is on. Now the car is approaching the edge of the lane, and there is a high-speed car going at the next lane and getting closer and getting closer. Now, ending this, and given that there is a threat event that the LKE is using fuzzing is disabled, and the reaction is that of the involved person is that the driver, and this is what's really unique about SOTIF, is that it takes in account the driver. So the driver does not notice that the LKE is disabled, so he's counting on it, but he doesn't notice that it's disabled. And the car, and hence the car is exiting the lane to the next one. Now this is scene 1. We go to scene 2, and we start from what we have ended, that the car is exiting the lane. Now the LKE is off, and the car is crossing now the edge of the lane, and the other car is really approaching. So the car in the adjacent lane is approaching. Now this neighboring car is going with a very high speed, and the driver do not take control on the steering. He may be panicking, or he may be even not noticing that the LKE. He may have his eyes somewhere other than the road, and hence a collision had occurred. Now we started building the scenes, and this is scene 1 and this is scene 2. And before we look at the demo, we have to step back a little bit, and I'll hand over to Amr, who's going to explain how did we reach the machine learning model, how did we reach to the design method for the machine learning model, what was the other available choices, and then we'll take a look at our demo. So Amr, I'm handing over to you. Go ahead.
Hello, good evening. This is Amr from AT Instruments. I work as an AI researcher. Today, quickly, I'll discuss with you how we reached our solution. It will be a quick technical journey. We firstly will discuss the nature of the problem we are facing. Then we will discuss the already existing solutions in the market. After that, we will proceed with our choice and the results we obtain. Okay, firstly, in order to find a solution to the problem explained by Mustafa, let us first extract the main features and challenges that are introduced by the automotive industry today in terms of cyber attack or cyber security, and also user misuse. So firstly, the first rule is that we always have new patterns of attack. Like static solutions will not be convenient. Secondly, the risk sometimes is hidden in the context, not in specific frame. So we are searching for a solution that can understand the context, not only point detection or point analysis methods. Thirdly, the risks could be caused due to cyber attacks or user misuse. And despite that the resultant damage could be equivalent in both cases, but the way of detection is very different. This will be discussed in details in the following sections. And also, the solution should respect the real-time style of the problem. Okay, so the model should be fast, should be responsive. Whatever the method we will choose, we should take this in consideration. Okay, firstly, these are the group of solutions that already exist. We have the signature base that was already introduced by Mustafa. We have something called physical printing techniques, and entropy-based, message parameter-based methods, and machine learning methods. We will talk firstly about the signature-based. We will not talk much about it because Mustafa already have covered it. But what we can briefly say about the signature-based is that it use the already known attacks to extract their malicious pattern to be used for future events. And despite the high ability of attack detection introduced by these methods, they are unable to deal with new attacks. So these methods act actually as a treatment method rather than a prevention one. A good example of the signature-based methods is the message authentication code. This technique was successfully applied in network security. It depends on cryptography. Briefly, in Mac, each node encodes the message it sends using various techniques. This will allow the receiver to ensure that the source of the message is legitimate. Okay, this is the game of authentication. And due to the high ability of these methods in internet security, many researchers aim to borrow this idea and apply it to in-vehicle security. But the problem they faced was that the maximum payload length in CAN protocol, which is used in vehicles, is 8 bytes only. Therefore, the ability to append extra ports to the frame was very complex. Some tried to truncate the extra port on few frames. This led to the need of large amount of computation power, which is computation power in vehicles is somehow limited. This led to high message latencies. This also led to high bus utilization. And after all of this effort, MAC method cannot solve the denial of service attack. So this is a quick glimpse about the signature-based techniques, specifically the MAC method. In the second board, we will talk about the fingerprinting techniques. Okay, researchers aim to work on the concept of authentication. They couldn't apply the MAC techniques, so they tried to compensate the problems that were found by physical printing techniques, that was introduced by the signature-based techniques. So they tried to work on the authentication concept. How could they authenticate the nodes without the traditional method known already in the signature-based method? They will use the physical properties of each node. Again, this is represented, okay, physical fingerprinting techniques in this type, researchers worked on authenticating each node. Each node is, in our problem, is ECU in the vehicles, using different physical features. For example, some used clock-based intrusion detection systems. They use the physical properties of the clock. Others use the physical properties, which is, in their case, with the voltage properties of the ECUs. But before discussing the details of these methods, we prefer to point out to the limitation introduced by the solution that is based on the authentication concept. Okay, we will discuss the authentication concept itself. These methods could perform very well for many cyber attacks, but it will be unable to deal with the user misuse risks. Since in the user misuse risks, the legitimate user uses a legitimate property, okay, which lead to an ECU to send a legitimate frame. Everything is legitimate in this scenario. There's nobody is impersonating. There's nobody is pretending to be another node. It's just a misuse. A legitimate ECU is behaving in an unusual way. So it's the understanding of context is very important. That's the point where we pointed for. The misuse problem could result in an equivalent damage happened by a cyber attack. But the way we should detect misuse or cyber attack could be very different. So the authenticating concept techniques really could not deal with the misuse problems. Okay, let us go back for the mentioned methods. For the voltage-based intrusion detection system, it is proved to be a very useful technique, but it only can be applied in the physical layer, so it cannot detect application layer attacks. For clock-based intrusion detection systems, many studies were published to discuss the techniques and also propose methods to overcome this defense mechanism. There are also other techniques in this family, but same argument is applicable for them. Okay, until now we discussed the signature-based problems and the physical printing techniques, and they are all depending on the authentication concept. Now we will talk about the message parameter-based techniques. These techniques work on the frequency of the flow. Okay, in this part, they monitor the frequency. One type of this family work on the frequency of the frames. It was showed that if there is an attack and somebody is injecting frames in the stream, the frequency of the frames will increase. This is logic. So they can use the frequency level of the stream to be an identification key if there is an attack is existent. Also, remote frame technique uses the interval time between sending a frame and receiving a frame to detect if there is something happen in the middle. Okay, this method has the advantages of it has low overhead, high accuracy, and its drawback that it can be ineffective for unknown security threats, and also parameters may vary in different vehicle networks. Okay, the fifth family, which is the informatic theoretic based techniques, it depends on the concept of entropy from the probability. Entropy could be viewed as a measure of randomness or disorder. Then how researchers applied this concept to automotive. The internal communication of an ECU is usually in order, like we are sending frame A, then frame with ID B, then frame with ID C, and then frame A and B and C. Like this, and in order, and we go so on, A, B, C, A, B, C. So with injecting large amount of frames, large amount of malicious frames, this will lead to an increasing disorder, which will lead to a higher entropy number, which means that we can detect an attack. Okay, so the entropy concept is can be used in this way to as a sign of existence of an attack. The main advantage of this method is the low overhead. On the other hand, it requires high volume attack to work, which means it's relatively insensitive to a small number of injected frames. It also cannot handle the attacks where the attacker changed the content of the frames. So it cannot deal with the reply attack. The last family is the machine learning family. Machine learning and neural network-based solutions are widely used for various tasks. Mainly, their ability to generalize using limited amount of data make them a strong candidate for many problems. Therefore, machine learning-based techniques are considered the best choice in terms of working against new attacks that are not being known before. And also, they have high ability to understand the context if they are designed for this purpose. However, machine learning methods are undeterministic, which means that we may get an unexpected output if the model faced new environment. One extra drawback is that the way we develop machine learning models recently does not systematically evaluate the safety of the models, the safety of those models. These are briefly the already existing solutions in the market. Let us quickly remember the nature of our problem. We said that we will always have new patterns of attack. The risk sometimes could be hidden in the context, not in a specific frame. Risks may be caused due to cyber attack or user misuse, and we should respect the real-time operation of the vehicles. And by analysis, we found that those needs could be covered or satisfied the best by the machine learning-based technique. But we still face the drawbacks of this method. What can we do? We propose a safe machine learning model development. We will design our model to be context-aware, and we will use the SOTIF guidelines to develop a safe machine learning model. But then, what is the SOTIF guidelines? These are the SOTIF guidelines. This is the development cycle of our models. First, we start with the analysis. This was explained by Mustafa. We analyze our problem in the same way that was explained by Mustafa and proposed by SOTIF. And then we extract the trigger event. Trigger event is the important event which we will focus on and where we can decide if there is a risk is occurring or not. In our case, the trigger event is any LKA transition from on to off or off to on. And we will use this info to design our model. Our proposed model, its main objective is to evaluate or classify each LKA transition that occurs in the vehicle. as an anomalous or normal transition. And then the verification phase, we test the model against what we can say daily events, unusual events that could happen, normal and abnormal, but usual daily events. In validation, we test the model upon more complex events, like you can imagine it as an eclipse, as a sudden rainy day, like suddenly thunder or something like that, and a very noisy input is one example of this. But we should understand the difference, like the sensors are still working, okay? Okay, anyway, in validation, for summarization, we will say that it works upon very complex cases. These are our results in verification phases. We worked on
Well, it looks like we lost Mustafa again. He'll be back shortly. Just really interesting discussion going on about using AI as a detection mechanism for security and safety anomalies. What I think I was talking earlier about the different projects that we have going on at ASRG. And one of the projects I mentioned was the member portal, but we also have started an intelligence platform. The intelligence platform will be available through the member portal. It seems that Mustafa is back again. Mustafa? Yes, can you please share your screen? Sorry for the technical difficulties, everyone.
Yeah, when was what was the last thing you saw, John?
I think one slide before this, and if you can remove the meet.google.com.
Oh, yeah. This one.
Thank you.
Okay. Okay. So this slide is already explained, right? This slide is done, right? Did you hear about the results, John? Right?
No, we didn't hear about the results. Can you go ahead and just explain it again?
Sure. Yes, I'm Omar and I'm back. As we said, verification is testing the model against usual and daily events that happens daily. It could you imagine every day? In validation cases, we test the model against extreme cases. We said like thunder, like eclipses, like very noisy input. So in verification, like normal cases, I mean by normal, like usually. I don't mean by normal like normal and anomalies for machine learning guys. I mean normal like usual, daily to daily events. We were able to successfully separate the normal from anomalous data or transitions with accuracy of 100%, as we show. In validation, the more complex events, the accuracy dropped down to what is still high accuracy. This is the summarization of our results, and Mustafa will handle back the presentation. Thank you.
Okay. So let's take a step forward in going through the Cpyr solution. So as we now know that there is a model that had been implemented on the GPU, and now that we have a red team that are introducing new cyber attacks, these cyber attacks are generating new data sets than the ones that had been the card trained on. Now, that once there's new data sets, there are always ongoing training happening. And once there is this this trained model had been finalized and is making good results, then a deployment then a deployment of the model will be done through the cloud, of course, with the coordination or the direct command of the SOC operator. Now, there will be a direct following. So we're going to show you some of the analytics that are being uploaded on the cloud. So in the demo, right in the next few minutes. So the analytics are being uploaded on the cloud and being visualized. In our demo, we're going to let you see the visualization on Power BI, which is a very at the market common tool. So the SOC will be able to see what's happening second by second at a certain core, if he's interested in a certain core. And he will be able to adjust the alarm level. So if he sees that there is a lot of false positives, which is something that's known in the machine learning, or there is some problems in the alarm level, then he will adjust. He can adjust just using as the delta OTA. He can adjust the alarm level of a certain core or an entire fleet. So this is basically what will how the model will be working, or how the new IDS framework will work. How we imagine it will work. Okay. Now, before we go to the demo, we have Cpyr is part of the Eyedrive framework. Eyedrive is a complete framework to monitor the car. So you can actually select a certain car, whether it is a driver, whether it's a user, a normal user, whether it is a fleet manager in a certain company, or whatever, or whether it is something like a mobility as a service company. It could select a car and it could make a video stream. It could directly stream a video up to 8 cameras per car, or record, or doing stream analytics, as we earlier said, that it could upload stream analytics, and so on. So Cpyr is part of Eyedrive, which I'm going to show right now. Okay, now let's go to the demo. So, as you can see here, let's open this here. Let's open this one. And so basically, we have, this is Eyedrive. This is our application. As I said, you can select the car of interest. Let's say this one. And you have here all of the options. So you can do video recording from this car. You can do stream directly from a car. You can actually do, as it says, GPU based inside the car. You can actually do passenger detection, passenger emotion detection, plate number of the different plate numbers of the neighboring cars. You can actually do some kind of passenger detection, and so on. And what of interest is our anomaly detection. This is Cpyr. This is basically the button that will fire Cpyr. Okay, so let me press on it. Once I press on it, then what will happen is that the cloud will be triggered and it will ask the GPU to upload. Please start streaming to me your analytics. Tell me how well things are going. So so let me just, and I just pressed on it, and I will refresh, and it will before it starts streaming the analytics, it will take some seconds. So until things are loaded, let me just tell you about the video that you're gonna see as well. So as I said, we're gonna stream the analytics from a core. Now, what we want to do now is showing you a complete demo as well. So first, let me tell you about the simulation. So the simulation here is, we have an LKA, as I said, a lane keep assist, which is driving in a lane, and it's preserving its designated lane. Okay, this is a simulation. There are many simulation tools. You can pick any one that you would like. They're all great tools. And now on our canoe, we injected a fuzz attack at this level here. Once we injected a fuzz attack, then this is the behavior of the core. So, and at this level, at this point where we injected the fuzz attack, a certain anomaly has been detected. This is at the GPU side. So these analytics are what's happening inside the GPU. And now here at this level, the analytics are being transferred real time to the cloud on Power BI. So this is what we're going to see at the video. Now, hopefully, our cloud Power BI has started to, yeah, not yet. We're still waiting to start. Hopefully, when we refresh it, the loss will start to be calculated. So what we did is that we triggered now the GPU to start reading. We have a GPU running, and as the GPU is running now, we have a canoe log inside the GPU with the anomaly. And we just and we have triggered it on our mobile application. As I explained before, this is the emulator for our mobile application. So yeah, so let's just wait a couple of seconds more or something. But maybe we can look at the video until the loss had been calculated for the AI model. So yeah. Sometimes it depends on our internet connectivity. So yeah, as I said, this is basically the demo on the video. So as you can see, this is our car. It's moving on the LK. It's moving inside the lane, and as we said, that there are some problems at our steering. And this is the canoe, and of course here is different and here is the Cpyr box. We call it Cpyr box, which is a model that's running inside the GPU. And this is the Power BI. This is on what we are monitoring on the cloud. So we see now that the car is starting to divert, and the LKA, however, had returned the car to its original position. And the car now goes to the other side. And now here there's a fuzz injected now. So we injected it through the canoe. And once the fuzz attack has been injected, we start to see a clear anomaly here at whether it is on the Power BI at the cloud or at the GPU side. So this is how the SOC operator will see and monitor the fleet, a sharp edge indicating that there is something going on. Okay, so this is how. Okay, now finally. The loss here is being calculated now at the Power BI, so it's being sent from our GPU backend, from our GPU board that is calculating the log. And as you can see here at the Power BI, it is which is connected to the cloud. You can actually see the dashboard. Of course, when we finish the entire, of course, I'm not gonna display the entire log for such a scenario, but I'm just giving you a glimpse of how things would work. We'll have a mobile app, or just the app at the operator side. He can trigger the anomaly. If he wants to monitor what's inside the car, he can do it. He can see different types of, he can stream the video, he can record the video, he can actually check if who's actually inside the cabin using passenger detection without the need of a huge traffic because of video streaming. You can see the plate numbers, you can see the plate vehicle, you can send vehicle detection. As there are many cameras, you can have up to 8 cameras, and yeah, with different views, and all of this will be streamed. Okay, by this I'm ending my presentation. I would like to thank you all. I'm returning back to you, John. So yeah, so thank you, and any questions open.
Okay, then at first, my name is Sven. I will moderate the question and answer session. So at first, also thank you from my side, Mustafa, for this interesting talk today, and also the details you explained. We received a couple of questions, interesting questions, and that's why I would like to start. So the first question comes from Mark. What impact will this have on performance of the vehicle? Specifically increase the message traffic or processing, and are additional power elements required to carry out the monitoring and reporting functions?
Okay. Regarding power, it's of course having a GPU processing is an increased power, definitely. It will not be a huge, of course, power dissipation if you have one GPU on the entire vehicle to monitor the entire vehicle performance. Then one GPU wouldn't be that huge power. Of course, there are. Of course, you don't need to buy a specific GPU because, for example, TI has its own board, has its own EC controllers with a GPU embedded inside, so you can do your processing as well as the GPU or AI models that you would like to add, like Cpyr. There are many suppliers who are offering both a normal processing power and the normal conventional processing elements, plus a GPU. So, and of course, but the GPU normally in the GPU has its own power rail because it's because there are additional power supplied. So you can have it inside inside your ECU, inside one of the processors on the ECU with a GPU capability inside, or you can have it monitoring our vehicle at the gateway level. This is regarding the power. Regarding the messaging inside, we used, as I said, we used MQTT. And maybe you have noticed that we were sending, the GPU was sending messages, and the streaming of the messages didn't have a huge problem. There was, I mean, once you get it triggered, once you get the car triggered, the data is being sent quite with. I mean, there was not a huge latency, I can say. I mean, for example, there won't be like a 10 minutes difference between what's happening inside the car and what's happening and what you're monitoring at the operation center. So this is there's going to be a maximum of a minute if you have a normal LTE mobile connection or something like this. Yeah, I mean, this is basically regarding the connection. Messaging, you can tune it. You can have, you can tune how much you want to see from the model. Amber, if you, I mean, basically, it's you can have, you can monitor on a certain parameter in the model. You can have a certain parameter selected, and you want to monitor this. You can just have, as we said, as you can see at our model, we just wanted to calculate the loss. And this is just a corner case. We just wanted to calculate the loss of the model. And based on the loss, we made the judgment that there's a problem. Once you just want to measure the loss, it's a very small data. It won't add a huge bandwidth to your requirements.
Okay. And regarding the processing, do you have some information, maybe how much runtime must be free to install your system on a typical GPU, which is used today?
Well, we used a Pascal GPU, which is an old architecture, and we wanted to do it on an old architecture, which so that we can check on the performance. Of course, now there are much stronger GPUs with much more gates, which much more millions of gates. Offered, for example, from our partners, or from, sorry, not from our partner, but from, as we are at the NVIDIA Inception program, NVIDIA are offering far higher GPU processing power, but we just used the Pascal, and it was enough to launch.
Mm-hmm. Then the next question: what's your idea regarding connectivity? So will the rules be updated at any time? And is the assumption that the vehicles will have also connection at all time, or maybe you manage the connection and make the channel only working if there should be information transported or something like that?
There shouldn't be any kind of modification at the communication. So if, so for example, if a certain OEM has its own infrastructure, and for example, it's sending a telematics control, telematics messages. So we based our messaging on MQTT, which is very widely used at the communication for different OEMs and for different IoT to talk in general. So so there shouldn't be any kind of modification at the communication. And as I said, you just need to modify what exactly you want to log from the model. And this is very flexible at Cpyr. But you have to say what you want to monitor and how deep you want to monitor the model. Once you get this figured out, and of course we can help you in this, we can easily say how much bandwidth it will take as an additional bandwidth.
Okay, thanks. Then coming to the machine learning techniques. So Raul wants to know if you can say some words which techniques you are using, and would it needed to have a training set that is driver dependent? Sorry.
Driver dependent or driver independent?
The question is if it is needed to have a set that is driver dependent.
Okay, I think we stayed in the level 3 automation level. When we introduced the misuse problem, I think the misuse happens when you already have two controllers, the machine and the driver himself. And this interaction sometimes cause problems, as we said, critical scenarios. So to reflect this interaction, you will use you will need the driver-dependent data sets to reflect that control transfer from the user to the machine or from the machine to user. So yes, We will still need this. And also, I think in higher automation levels, there will be critical phases where you will make the user handle them. So you don't want your machine learning models to perceive this as an anomaly. This is a critical case, and you decided to give the user the control. You don't want your all AI models in the car to perceive this as an anomaly. So you will always need, I think, a driver-dependent data sets.
Okay. Then if we look around the world, we have different regions, different cultures, and also different driving styles. So with respect to this, what's your experience? How long it would take the training period if we think to the differences that we have in the different parts of the world?
Okay. To get as much training sets as possible, this means as well to have different drivers as well. First we need to have a model. So basically, we need to have a model for the car at an ideal situation, at an ideal driver, a normal driver, which is, let's say, 60% of the drivers will behave in this. Then we need to have, of course, we need to have different users to try it on. So, for example, we know, for example, that different car manufacturers go to Sweden in order to do some test drives in very steep slopes, for example.
Yeah.
This is one variant, of course, is how different the roads. Of course, we know that there are different road tracks in Canada and in Sweden that are built specifically just for autonomous level training. Also, there is the second thing is actually to introduce drivers who are the spectrum of different drivers. So, for example, if an old lady needs to, we need to try to modify this behavior a little bit. This is one case just before production. Before production, in all cases, every OEM will need to train its model. It will need to do test drives. So everybody is doing this in all cases. The additional step is that besides doing these test drives, you just add the model inside. You add Cpyr inside as an ingredient, and let the model train itself by itself. So let the model train while you're doing the test drives. Besides this, you can actually, of course, this is before production. After production, there is a monitoring, and there is always a cycle of training after production. Amr, if you want to.
Okay, and I think also, yeah, this is a problem dependent. Okay, sometimes the behavior of the user is not that different. Okay, yeah. For example, in a very different domain, sentiment analysis models. These models is used to understand the feeling of a person. Okay, happy, sad, and things like that. But despite everyone has his own way of expression, we develop a single sentiment model, and it works on many people. So it's a problem dependent. There are some problems, the inputs are very limited. The behavior of the user is very ineffective in this case. So we will not need a purely different model. On the other hand, if we needed to change the model from one person to another, I think the core functionalities that exist in the model will not really change. We may use fine-tuning per person. In the last layers, this is a little bit technical, but if we have like deep learning and many layers, the core functionality lies in the code layers. Okay? We most probably, I think that we will not change we will not need to change those code layer parameters. It will be fine-tuning at the last layers. This takes much less time, and it's, I think, efficient as it is not a change from a function to another. It is a change from one person to another. There will not be a huge gap between people. So I think the model will not really need that much change, and in general, it will be problem dependent. And we also does not need to change the training processes. There are some hyperparameters around the model after production that we can control them to manage the operation of the model without really retraining the model per person or per area. That's my answer.
Okay, so thanks. There comes now also regarding to the explanation an interesting question. So what about a left-hand drive and right-hand drive? So normally by the car, this is the same model and so on, and this will be handled via variant coding. And maybe then it's also the same ECU inside the car where your model is running on, but makes this a difference, or is the intelligence at this level that this can be handled automatically?
I still think that the same model will work for both sides, because left hand or right hand, it watches the distance from the lane. Okay, we can say that our model is prepared to avoid collision right side, and when it is on the left side, we don't care. It's designed to avoid the collision on both sides, and I don't think the behavior of the user will change when he is left driver or right driver, depends on the country. So I think the behavior of the user will be the same in both sides. Both will try to be at the middle of the lane. Both will avoid collision at the same level, whether it was at the right side or the left side. So I don't think, at our problem at least, this will be a cause of huge difference.
Okay.
And,
thanks for that.
A practical observation adds up to us. Maybe this is our first intuition when we set up this model, because practically we found other solution. That's why our analysis methods and softwares are useful. We will see, maybe this will cause something. And thank you.
Okay, then the next question is also interesting. If we think on a fleet, so one type of car which is sold in every region in the world, do you collect the data and train your model with the complete fleet, and you will also then share the trained model over the world? So this is related, of course, the post-production phase.
Okay, could you re-say the question, please, again?
Yeah. So if we think on a fleet and the post-production phase, so where you improve your model or the rule set, do you collect the information from all the cars that are where your system is installed and which belongs to the same model over the whole world? And if you improved your model and your rule set, and you make an update, is then the same model or the same information shared with every car all over the world?
Okay, I think yes, if there's no huge difference in culture in driving, as the first question said, I think yes, this will be used. We can harvest data from different countries, from different cities, all over the world. And as long as it does not have, as we said, difference in driving styles, or it's still problem dependent. If the shape of the roads is different from country to another, this will our ability to use the same data from this country to this country. But as long as we have the same culture of driving, as long as we have similar environment, we talked about the validation problems, or the testing the model against complex problems. Maybe the environment is very different, Europe from Africa. So if I'm testing something or developing a model and depends on the environment level, okay, like a camera or something, this should be very considered. It's very unusual to have snow in Africa. I won't use this data if I'm training cars for Africa. On the other hand, if it's an ECU issue, I think noise may happen in both environments, Europe and Africa. The same behavior of ECUs could happen. So I imagine that use this data from all over the world to train the model at this level, the ECU level. So it's a problem dependent, it's an environment dependent. We try to use the common data, yes, harvested from anywhere in the world.
Okay, thanks for that. So let's discuss about the last question now. So there are several companies available in the market and also startups which are looking deeper in this machine learning and artificial intelligence methods as well for security detection or intrusion detection. So what do you think, what is the advantage or some kind of unique selling point for your solution?
Okay, the unique thing about our solution is that it doesn't take the car behavior. Most of the, let's say, most of the AI machine learning intrusion detection systems are actually looking at how the car behavior. Okay, what we do here is that we have not only do we depend upon what's actually in the messaging or whatever kind of the ECU behavior, we are actually looking as well on the driver himself. So we have cameras that are, as we said, on Eyedrive, that are looking at the driver and at the passengers and even at the traffic itself. And all of this video streams are being processed at the GPU as well as the ECU behavior. So we're not only looking at the ECU behavior, we're looking as well on the driver himself and at the entire environment. As SOTIF introduced the new method, that SOTIF did not only say that not like ISO 26262. We are going to look at the ECU behavior. No, SOTIF said we're going to look at the driver behavior and we're going to look at the environment behavior, and we have to take this into consideration. As this is what we are doing as well here. We are saying we're not going to look at the ECU behavior only. We're going to look at, of course, at the ECU behavior, and we're going to look at the messaging behavior and everything, all of this. But not only this, we're going to look as well on the cameras, on the driver, and what's going inside the cabin, what's happening outside the cabin, and all of these video streams are being processed at the same GPU. Now,
Okay.
Of course, all needs to be trained and to have a concrete model for everything together. This is the hardest part, but the most interesting part.
Okay, then thank you also for pointing this out. Again, thanks for the presentation and also the answering the questions. It was as well very interesting. And now comes the time where I want to give the word back to John to find the final words for today.
Yeah, guys, thank you so much for being a part of ASRG. Actually, this was really a great presentation. Really interesting, and thank you to the audience also for giving some questions. Really nice discussion. So, guys, before we close for tonight, would you like to say some closing remarks?
Yeah, just, I mean, really thank you for your attention, guys. Really thank you for your time. Some really interesting questions. I mean, and to the point questions. I mean, this is a very, very engineering questions. And of course, thanks, John and Sven, for giving us such an opportunity. It's a great pleasure to be at ASRG. And of course, we would like to thank NVIDIA for helping us a lot as we are in the Inception program. So, yeah, thank you for your time, guys. Thank you. Thanks, everyone.
Yeah, great, guys. Thank you so much. What a great presentation tonight. Just reminder, we have some great presentations coming up in the next few weeks. Please come back, check out the YouTube channel for ASRG, check out the website. Get involved. This is a growing industry. Anyone can be a part of it, and ASRG is here to help you do that. So thank you very much. We'll see you soon. Have a good night. And